Local Maxima and Local Minima. Hello everyone. To begin today's lesson, let's first look back at what we covered in the previous subsection, where we explored the concept of absolute maximum and minimum values. As you recall, these absolute values refer to the absolute highest and absolute lowest points that a function reaches across its entire domain or within a specific given interval. However, when we apply mathematics to real-world analysis, we find that functions are rarely that simple. In practice, graphs often fluctuate, creating multiple peaks and valleys along the way. This is where the concept of local extrema becomes essential. Over the next few slides, we will define exactly what these are and how they differ from the absolute values we have already discussed. Understanding the concept of a neighborhood. Now that we have introduced the idea of local extrema, we need a precise way to define them. Before we move on to the formal definitions of local maxima and minima, we must first understand a fundamental concept called a neighborhood. In mathematical terms, a neighborhood of a point, which we will call point C, is simply a small open interval that surrounds that point. We denote this interval as the range from C-h to C+h. To clarify, the letter h here represents a very small positive number. You can think of h as a tiny distance that extends both to the left and the right of point C, creating a small zone around it. The reason this is so important is that it changes our perspective. Instead of looking at the entire graph across its whole domain, which is how we identified absolute maximums and minimums, we are now focusing only on this small window. By restricting our view to this specific vicinity, we can determine if point C is the highest or lowest point relative only to the points immediately surrounding it. This sets the stage for our next few slides, where we will use this neighborhood to formally define local maxima and minima. Point of local maxima. Now that we have established the concept of a neighborhood, let's apply it to define a local maximum. A function, which we will call f, is said to have a local maximum at a specific point, C, if the value of the function at that point is greater than or equal to the values of the function at all other points within its immediate neighborhood. To be more precise, let's look at the formal mathematical definition. A point C is considered a point of local maxima if there exists some positive number h, such that the function of C is greater than or equal to the function of x. For all x values falling within the open interval from C-h to C+h essentially. This means that if you look at a tiny window around point C, the function reaches its peak right at C. Finally, it is important to distinguish between the location and the result. While C is the point where the maximum occurs, the actual output, f of C, is what we refer to as the local maximum value. In the next slide, we will explore the opposite of this concept, the local minimum. Point of local minima. Now, let's look at the opposite side of the coin. Just as we have peaks, we also have valleys. Conversely, a function f has a local minimum at a point C if the value of the function at that point is less than or equal to the values of the function at all points in its immediate neighborhood. Essentially, if you look at the small window we discussed in the previous slide, point C is the lowest point in that specific area. To put this into a formal mathematical definition, a point C is considered a point of local minima if there exists some positive number h such that the function value at C is less than or equal to the function value at x, for all x within the open interval from C-h to C+h. In this scenario, the actual output of the function at that point, which we call f of C, is referred to as the local minimum value. While these formal definitions can seem a bit abstract, they become much clearer when we visualize them. In the next slide, we will explore the geometric interpretation to see how these local maxima and minima look like a landscape of mountains and valleys. Geometric interpretation. Now that we have established the formal definitions and the concept of a neighborhood, let us move toward a more intuitive way of visualizing these ideas. I want you to imagine the graph of a function not just as a line on a coordinate plane, but as a physical landscape consisting of mountains and valleys. First, let us consider local maxima. You can think of these as the tops of hills. To put this into perspective, imagine a person standing at the very peak of a hill. In this scenario, that person is at a local maximum. They are the highest point relative to the ground immediately around them. However, it is crucial to note that while they are at the top of their specific hill, there may be much higher mountains elsewhere in the distance. Those distant, highest peaks would be what we refer to as the global maxima. Conversely, local minima can be visualized as the bottoms of valleys. If a person were to descend into a valley and stand at its lowest point, they would be at a local minimum. At this position, they are at the lowest point relative to the slopes immediately surrounding them. By using this landscape analogy, we can clearly distinguish between a point being the highest or lowest in its own small vicinity versus being the highest or lowest over the entire domain. This distinction will be very important as we move into our real-world example in the next slide. Real-world example: daily temperature fluctuations. Now that we have visualized these concepts as hills and valleys, let's apply them to a real-world scenario to see how they work in practice. Imagine we are tracking the temperature of a city over a full 24-hour period. We can represent this as a function, t of t, where t represents the time in hours. Let's look at a specific scenario. Suppose the temperature rises throughout the morning, reaches a peak at 2 p.m., drops slightly in the evening, rises again due to a warm front at 8 p.m., and then drops overnight. Let's analyze this step by step to identify our extrema. First, let's look at the first peak. At t equals 14, which is 2 p.m., the temperature is 35 degrees Celsius. If we examine the immediate neighborhood, meaning the temperature at 1 p.m. and 3 p.m., and find that those values were lower, such as 32 and 33 degrees, then t equals 14 is a point of local maxima. It is the highest point in that specific time window. Next, let's identify a valley. Suppose that at 6 p.m. or t equals 18, the temperature drops to 28 degrees Celsius. If the temperature at 5 p.m. and 7 p.m. was higher, for instance, 30 degrees, then t equals 18 is a point of local minima. Just like the valley in our previous landscape analogy, this is the lowest point relative to the times immediately surrounding it. Now, notice that the temperature rises again to 30 degrees Celsius at 8 p.m. or t equals 20, before falling once more. Because this point is higher than the times immediately before and after it, t equals 20 is another point of local maxima. Finally, this leads us to a very important distinction that we will explore in the next slide regarding common mistakes: the difference between local and global extrema. Even though 8 p.m. is a local maximum, it is not the highest temperature of the entire day. The global maximum for the day is 35 degrees Celsius at 2 p.m., because that is the absolute highest temperature recorded over the entire 24-hour interval. Common mistakes. Now that we have explored the definitions and seen a real-world example with temperature fluctuations, it is important to address some common pitfalls. Let's look at the most frequent mistakes students make when dealing with local extrema. First, be careful not to confuse local maxima with global maxima. A very common misconception is assuming that any local maximum is the highest point of the entire function. As we saw in our temperature example, a function can have several peaks, which are our local maxima, but there is only one absolute or global maximum value across the entire domain. Second, avoid the assumption that whenever the derivative of a function at a point C is equal to 0, you have automatically found a local extremum. While a zero derivative often indicates a peak or valley, it is not a guarantee. For instance, consider the function f of x equals x cubed. If you take the derivative at x equals 0, the result is 0. However, if you examine the graph, you will see that this point is neither a local maximum nor a local minimum. Finally, never ignore the neighborhood. As we discussed at the beginning of this lesson, local extrema are defined strictly by the behavior of the function in the immediate vicinity of the point. If you only analyze the function on one side of the point, you cannot definitively conclude whether it is a local maximum or minimum. You must consider the entire small interval surrounding the point to make an accurate determination. Keep these warnings in mind as we move toward our final summary in the next slide. Key takeaways. To wrap up our lesson on this topic, let us review the key takeaways to ensure you have a solid grasp of these concepts before we move forward. First, let's recap the local maximum. A point C is a point of local maxima if the function value at C is the highest value within a small open interval, specifically from C minus h to C plus h. Similarly, a point C is a point of local minima if the function value at C is the lowest value within that same small interval, from C minus h to C plus h. This brings us back to the fundamental concept of the neighborhood. It is crucial to remember that when we perform a local analysis, we are restricting our focus to a small region immediately surrounding the point, rather than looking at the entire domain of the function. This is the key distinction that prevents the common mistake of confusing local extrema with global ones. Finally, as a helpful visual cue, you can always refer back to our landscape analogy. Simply think of local maxima as the peaks of the hills and local minima as the bottoms of the valleys. Keep these points in mind, and you will be well prepared to identify these points in more complex functions.